Welcome to the training on European GNSS for the drone operators, where we will show you how to integrate and take a full advantage of the European GNSS, meaning EGNOS and Galileo and its services for your drone operations. Today, GNSS is an essential for navigation and positioning for majority of the drone operations. You will be guided during this training by our experts from Galileo Service Center and EGNOS service provider, and they will show you how to implement and really use the EGNOS and Galileo for your operations.
Welcome to this introductory video dedicated to showcasing the implementation and use of EGNOS for UAVs in different applications. My name is Sergio Cabrera. I work at the European Satellite Services Provider, the EUSPA, and my task involves representing the European Union Agency for the Space Program, EUSPA, on explaining the benefits of EGNOS for aviation and drones. In the next 15 minutes, I will go about what is EGNOS, I will provide you a description of it, and I will explain how to configure most common GNSS receivers on UAVs today. Also, at the end of the video, I will provide you with my contact details so that you can refer your questions to us in case you will find it interesting. So bear with me for the following time and get to know more about EGNOS. Let's start with the EGNOS part. The ESSP is the EGNOS services provider and therefore is the company in charge of providing all the EGNOS services. Also, we are in charge of acting as the link between the users and the system, providing support, offering assistance, and guiding them through the evaluation, use, and/or the implementation of EGNOS. On the system side, we have our customer, the European Union Agency for the Space Program, called the EUSPA. And then we have the design agent ESA and Thales Alenia Space as industry, which are the companies in charge of keeping the geostationary satellites in operation and their maintenance. As ESSP is providing a service dedicated for aviation, it shall be authorized by EASA to do so. Therefore, the Safety Authority EASA certifies ESSP as an air navigation services provider. This is the environment where ESSP stands and where EGNOS provides its services. Let's dig deeper into detail on what is EGNOS and ESBAS in general. EGNOS is the European Satellite-Based Augmentation System, and it provides an improved performance compared to GNSS. As of today, EGNOS augments GPS on the L1 band, but it is expected to augment Galileo in the future, and not only using L1 band but also on the L5 band. This is referred to as dual frequency multi-constellation, and it is expected for EGNOS version 3.2. The EGNOS signal sends differential corrections and integrity messages, which only need a compatible GNSS receiver to be able to use it. There are a couple of ways that you can plug into the EGNOS system architecture, and it would allow you to perform one or other types of operation. Digging down deeper onto the EGNOS system architecture, if we start on the right hand side of the picture, we can see that we have a range of ranging and integrity monitoring stations that we call RIMs. There we know very accurately where they are located, and we receive the GPS signal at all of those stations. They send all the information gathered through the E1, the EGNOS Wide Area Network, to the MCCs, the Mission Control Centers. At the Mission Control Centers, we process all the data gathered and we compute the signal that we need to send to the users in terms of corrections to the GPS signal. The EGNOS signal, once calculated, is sent via the NLES, the Navigation Land Earth Stations, which are just antennas pointing up to the geostationary satellites, which they bounce the signal back to the user. So at user level, the user will get the GPS signal on one side and the EGNOS signal on the other side. The EGNOS signal will work on top of the GPS signal to correct it and therefore provide a more accurate position solution, increasing also availability. Now, there are a couple of ways that you can use EGNOS. If you connect to the EGNOS signal in space, or what we call SIS, you will either be using the open service or the safety of life service. Their difference is basically the integrity concept. On the safety of life service, even though it will be still using the same signal in space, it also considers the integrity. And that means that the signal can be used for applications where lives of people can be endangered if the system fails. For drones, we typically refer to the open service. So, as the system is defined, the signal in space accuracy for the open service or even the safety of life service to the 95th percentile is 3 meters in the horizontal plane and 4 meters in the vertical plane, and that will be for the worst case scenario. On the other hand, if we connect to the E1, the EGNOS Wide Area Network, we are capable of using the EGNOS Data Access Service, what we call EDAS. Here we can receive data from the internet, and it will allow us to perform RTK, real-time kinematics. The accuracy performing RTK is in the range of centimeters both horizontally and vertically, but you will either have to be near a RIMS station so that you can connect to it and receive data from the internet, or you will need a base station to connect to it. So we wanted to compare the system definition with respect to the reality, and therefore we prepared some tests using our drone, our custom-made hexacopter, which will show us in reality which is the actual EGNOS performance. We programmed a kind of mission that is called dynamic pass-to-pass flight, or we call it dynamic pass-to-pass flight, which is programmed in the ground control center that we are using. In our case, it's Mission Planner, as you will see in some minutes. And this will be the path that we will command the drone to attempt to follow. Then we will configure the drone using EDAS, and it will attempt this flight with some kind of error that we will measure afterwards. Then we will command the drone to perform the exact same path but using EGNOS in this case, and then we will do the same but using GPS. So measuring the exact position of the drone and comparing that with respect to what we commanded the drone to follow, we are able to compute the total system error. On the left-hand side, we can compare the total system error to the 95th percentile on using GPS with respect to using GPS plus EGNOS. On the horizontal plane, we saw that with GPS only, the error was 1.5 meters, around 1.5 meters, and on the vertical plane, it was 2.6 meters. When we configured EGNOS also to be used, the horizontal error was reduced to below 1 meter, and the vertical error was decreased to just above 1 meter. Regarding the EGNOS Data Access Service, and for this particular test, it was noticed that we had very strong wind gusts. The total system error on GPS only, it is noticeable worse than on the other case, that is due to the strong wind. But on the EDAS side, we saw that horizontal and vertically, the error was 0.7 meters, which is remarkably better than using GPS plus EGNOS, and even considering that there's a strong wind, it provides a greater level of accuracy, even in poor weather conditions. If we highlight some examples of where EGNOS can prove to be beneficial, we can refer to inspection, measurements, photogrammetry, surveillance. These two ones, photogrammetry and surveillance, they typically indeed use one of the flight paths that we programmed on the drone. That is why we wanted to test it ourselves. We have also seen uses on search and rescue or public services, even delivery, that the accuracy of the signal is key for drone operators to make sure that the parcel is delivered to the correct land. And then also spraying, I may highlight. Agriculture indeed is lately gaining a lot of inertia in the use of drones. because their capability and efficiency on techniques which does not require a very high level of accuracy, such as spraying, can prove to be very beneficial for savings and also for time efficiency. This is the ESSP hexacopter. We typically connect to it using the USB mini port right here. This is the controller, and we will connect the GNSS receiver to the GPS 1 or GPS 2 ports right here. We are now using the GPS 1 and the signal goes to the GPS receiver. So all the commands are sent from the laptop to the controller and then they arrive to the GPS receiver. Therefore, in order to be able to use this, we need to create a bypass that would allow us to command the GNSS receiver to do as we want. Once it's connected, we will have to update all the parameters inside, so we will hit that right now. We allow the computer to download all the parameters and everything inside so as to make sure we will be able to connect to the GNSS receiver accordingly. So now that it is updated, we will pop up the hidden menu that we see on Control F, and then we will hit on the button Map Serial Pass. Once done, on port 500, we will have done a bypass. And now, at this moment, I am able to command the GPS receiver to do as I want through the proprietary application. In this case, it's a Newbox. So going to the UNCenter application, we can just go up here to the network connection menu and we type TCP localhost 500 that we can take from the hidden menu that we saw on Mission Planner. If it turns green, that means that we are connected, and then we can navigate to Messages View, then to UBX that we can expand, then we go to CFG for configuration, and then we navigate down to GNSS. We should be here. Let's expand the menu, and here is where we will configure this satellite constellations to be used. So we configure GPS, we hit on enable. Usually the minimum is 8 and the maximum is 16, that comes like that. On SBAS, same thing, we need to configure and click on enable. The minimum is 1 and the maximum is 3. You will only be using 2 geostationary satellites, but you can type 3 in any case. Then, as for the number of channels, you should have this updated accordingly depending on your GNSS receiver. So I would only recommend to put auto set. And then once the configuration is done, you hit on send a couple of times. It usually takes a couple of takes to actually send the information. So once this is done, we will navigate down to the SBAS setting. We need to make sure that the subsystem is enabled. We need to detick the test mode and apply SBAS correction data. EGNOS is at the moment not providing ranging, so we should detick the ranging tick box. And then going further down on the menu, we can select the number of search channels. We have 3 geostationary satellites, so we can put 3 channels. However, your GNSS receiver will use up to 2 geostationary satellites, so you may put 2 here as well. Now, and this is the tricky part, if you click on EGNOS, the geostationary satellites that are pre-configured may actually not be the correct configuration. So, in order to confirm so, what we need to do is select Other, and then go to the EGNOS user support website to check which are the geostationary satellites currently active. In the front page, you can see the EGNOS system status in real time, and in green we can see that we are now using the PRN 123 and PRN 136. So these are the numbers that we should type here on Other. 123, 136. Then we make sure we hit on send a couple of times to make sure the receiver receives the information. and it will be done.
Welcome to this introductory Galileo for Drones online training, where I will share with you the last updates of the Galileo services for drone operations and how to configure your drone on using Galileo. My name is Ernesto Llorente and I work at the European GNSS Service Center, the single interface between the Galileo program and all the global users. This training is offered under the management of the European Union Agency for the Space Program, EUSPA, and we really hope that you will take some valuable insights within the next minutes. Please, join me through this presentation. First of all, let's start with a quick remark on Galileo and the Galileo services for drones. Galileo is the European Global Navigation Satellite System. Today, most of the drone operations mainly rely on GNSS for positioning, navigation, and timing, PNT. We call Galileo differentiators those services already provided by Galileo. Today, we are going to focus in two of the most promising Galileo differentiators for drone operations: the Galileo High Accuracy Service, HAS, and the Galileo Authentication Service, OSNMA. Let's start with the characterization of the low-risk drone operations, mostly open category and specific category Sail 1 and Sail 2, according to both JARU's SORA methodology and EASA easy access rules for drones. The typical operation would be a visual line of sight over low-populated areas. These operations are performed in open sky conditions, meaning that we always have a high number of satellites in view. The typical drones involved are light and small, usually ready-to-fly CE class mark multicopters. We will review the list by EASA shortly. As for the typical GNSS architecture on board of these drones, we will find a single GNSS multi-constellation and dual or multi-frequency module. The manufacturers follow a black box approach, in the sense that the configuration are factory presets that most of the users and drone operators may not be able to change. So, what GNSS module is inside your drone? Well, typically, your drone's built-in GNSS receiver will be a multi-constellation module, compatible and concurrent with at least 3 of the 4 GNSS constellations. Characteristic that will help to reach improved accuracy, availability, and continuity, and also protection against single system blockades. Additionally, the module will be dual frequency or multi-frequency, capacity that enhances the PNT solution against degradation of specific frequencies. With both multi-constellations and dual-frequency multi-frequency capacities, the system can better mitigate the multipath effects. The GNSS embarked will probably be SBAS capable, so EGNOS should be compatible with, but it may not be possible to activate it if the factory configuration is not enabled. This is the list that EASA publishes in its web portal, classifying the different CE class marked drones of the market, typically ready-to-fly platforms designed to be operated in open category and low-risk specific category scenarios. So let's consider you are operating a CE class marked drone. Is it compatible with Galileo? Well, we have good news. All of the list CE class marked drones are Galileo enabled. And now, let's jump into the medium-risk drone operations, specific category Sail 3 and Sail 4 according to SORA methodology. These operations introduce new challenges to be solved and new requirements to be taken into account. If we pay attention to the Sail 3 operations, we are typically talking about beyond visual line of sight, over unpopulated or low populated areas. Here we will again find open sky conditions with occasional bad geometry. But in any case, some metrical accuracy may be required to define new aerial routes for drones. if we turn into Sail 4 operations, the urban scenarios will be introduced. And on top of SORA, the role of geospace can be decisive. The potential complexity of the terrains and the urban canyons may introduce mask angles issues. And the GNSS integrity will become a major requirement for most of the operations. In any case, it is a common and agreed that the drone operators will need to understand better and study in detail each operational scenario. That involves the technology and the operational procedures to mitigate GNSS interferences and signal degradation, and also targeting an increasing concern for aviation and drone, the jamming and spoofing events. It will be very important to report and share with the community. It is also recommended between the working group in standardization to carry out some GNSS performance forecast analysis for the sake of safety. The typical drones involved in these operations are light and medium-sized hybrid eVTOLs and multicopters, carrying payloads and transporting goods. For the Sail 3 operations, EASA is planning to publish very soon a list of pre-qualified drones, while for the Sail 4 operations, the pre-qualified drones still follow a design verification review, the DVR. And if we turn into the typical GNSS architecture that we will find on board of these drones, this is a multiple, multi-constellation and multi-frequency GNSS module configuration, meaning that they are introducing redundancy at this level. Additionally, high-accuracy embark technology and authentication features against external threats are being implemented. At this level, the drone operators may be able to change and configure settings that will better fit their final use with the support of the manufacturers. Higher risk drone operations introduce new challenges and new requirements for drones. Let's target the high accuracy challenge for drone operations. New drone applications as drone delivery require higher levels of positioning, navigation and timing accuracy, and also improve coverage, availability and continuity during the whole drone operation, typically in BVLOS scenarios with a changing environment. Galileo provides a solution to this challenge with the high accuracy service HAS. This service is transmitted to the drones either directly from the signal in space, either from the Internet Data Distribution (IDD). It is a free of charge and global PPP service that offers accuracy of few decimeters in each plane. It may become a game changer in scenarios that will request high density of BVLOS drone operations. The GSC website published a list of receivers implementing Galileo HAS for many different applications. Out from that list, here we present those devices potentially suitable for drones, either embarked as a payload, especially those ones that are bigger in volume and weight, either integrated in the navigation core, more compact and light. This list is not exhaustive and is being regularly updated. So, how to activate the HAS service for your drone? From the GSC, we provide guidance and support, and here we will briefly introduce some common steps for Galileo HAS activation. In any case, it is recommendable to contact each manufacturer and get specific support. Currently, the HAS for drone projects are being announced using customized drones and also ready-to-fly drones with sufficient payload capacity. Most of the activities involve the PNT signal recording and post-processing with HAS corrections. The common steps include upgrade of the GNSS receivers and the drivers firmware, so the previous setup should be as a ground test in open sky conditions to check that all the elements are HAS capable, including a compatible E6 antenna. It is important to embark a memory card or a data logger in case that we would like to post-process the HAS data. Additionally, to get the Galileo HAS via IDD, it is advisable to register at the GSC website and request the access and credential from the HAS Entripcaster. Again, direct support from manufacturers may be helpful at this point. It is expected that the next generation of drones will benefit from the Galileo has features directly from their integrated GNSS modules. A very different challenge and a major concern not only for drones, but for the whole aviation operations, are the increasing GNSS spoofing and jamming events. Spoofing is a sophisticated form of interfering and falsifying GNSS navigation signals. GNSS signal falsification can have disastrous impacts on applications and market sectors that rely on precise navigation, such as drones. Galileo provides a solution for this challenge for drone operations: the Open Service Navigation Message Authentication Service, in other words, OSNMA. OSNMA is a Galileo service providing a GNSS embed feature that ensures the secure end-to-end transmissions from Galileo satellites to GNSS receivers. With this Galileo differentiator, it is possible to protect the authenticity of navigation messages transmitted by the Galileo satellites, enhance the reliability of GNSS positioning and timing, mitigate spoof signals by selecting others, and even cross-check other constellations. Again, we invite drone operators and integrators to visit the GSC website, since there is a list of receivers implementing Galileo OSNMA. As an extract, here we can see some of the OSNMA-ready modules suitable for drones, either at the navigation core, compact at light, either embarked as a payload. The GSC has specific information and steps for the configuration of some OSNMA-capable receivers for drones available at the center. This list is not exhaustive and it's being regularly updated. How can you activate OSNMA in your drone receivers? GSC provides support for manufacturers, integrators, developers, and advanced users in order to get the last available cryptographic OSNMA resources for the receivers. The intention is the final users should only focus on checking that the service is already operative in their platforms, while they still can get support either from the GSC and either from the manufacturers. There are also some available public libraries in internet that should help to understand the service and its current performance, showing for any specific point of the globe the Galileo satellites in view at a specific instant against the Galileo satellites transmitting OSNMA. That means those that are authenticated. The good news are that OSNMA service is transmitted by the Galileo E1B frequency, meaning that the service is potentially compatible with several GNSS receivers that are already in the market. But they may require a firmware upgrade, and this is not always possible. In any case, it is expected that the next generation of mass-market drones will integrate OSNMA as a preset configuration by default. Currently, the OSNMA for drone projects are being announced using customized drones and also ready-to-fly drones with sufficient payload capacity. As for the OSNMA visualization, it is and its mode. Typically, it is useful to compare the visible Galileo satellites in view against the OSNMA authenticated Galileo satellites during the mission. In that regard, depending on the criticality of the mission, different OSNMA modes can be activated. The loose OSNMA mode, that in the PNT solution is taking into account both the authenticated satellites and the unknown authenticated satellites, and the strict OSNMA mode that only takes into account the authenticated satellites for the PNT solution. For example, in the example below, we had a range of 9 to 11 Galileo satellites in view, while the OSNMA authenticated range was between 6 to 9 of them. A strict configuration, taking into account less satellites considered for the PNT solution, may lead to a less accurate solution, but also to a more reliable one. So, summary up for the Galileo for drones, we will review that Galileo is the Europe's global navigation satellite system. It provides accurate, reliable, and precise positioning, navigation, timing, and safety services. Galileo is designed to provide Europe and the European citizens with independence and sovereignty while creating a multitude of services and applications across different sectors, including drones. And we have to remember that the Galileo differentiators, as Galileo High Accuracy Service and Galileo OSNMA, are very promising services for drone operations. It is expected that these services will be integrated and enabled in the upcoming generation of ready-to-fly drones and the GNSS modules for advanced drone applications.
Thank you for joining us at this training. I hope that you've got useful information on how to integrate European GNSS in your drone. We also do in-person practical trainings at the major drone events and conferences in Europe and also in different member states per request. Feedback is welcome, and we encourage you to check our EUSPA websites on more drone activities.